much time we have? Okay, then we can go back to the integral formula. Right. Integral formula is also important because many applications actually using that formula, like statistical mechanics. Sometimes we're using this formula for, I think it's there's some exercise. I think it's the Fermi distribution, or yeah. If you use the Fermi distribution, sometimes you need this kind of integral. So you see that application, the integral form applied to some physics problem. But we'll look at this integral forms. So this is just a discussion of showing this another Dirichlet series. So once we did that, we know that we can extend that to we'll see greater than 0. So that's important. And now the integral form is gamma z. So e at t to the z minus 1. There's some very similar to the integral form of the gamma function, and e to the t minus 1. But this is e. E. Okay. Right. The difference is that if you don't have this minus 1 factor, this is exactly the same. This part is the same integral representation of the gamma function. The difference is this minus 1 factor, minus 1 term in the denominator. You don't have that, let's get back to the gamma function. Okay, and now to show that this is the same as this factor, we can do an expansion. The expansion, because t is from 0 to infinity is positive. I mean, at least that's the formula defined, right? And so, and then we can make it a series of small factor. If we just divide e to the t for both numerator and denominator. So you have t minus c minus 1 e to the minus t. And so might basically multiply e to the minus t to both numerator and denominator. And this factor becomes 1. This term becomes minus e to the minus t dt. Right. And e to the minus t is a number that is less than 1. Right. So so you can do the expansion over this 1 over this 1 minus c e to the minus t factor. And the turns out to be infinity, keeping everything first. And this is the summation. Let's see. This is the summation. So basically 1 minus x. What is 1 minus x? We talk about that. 1 minus, you remember what is 1 minus x? The expansion is 1 plus x squared plus x cubed, right? All the factors. We write a summation, it should start from m. I mean, it should start from 0, but I'm a little confused with your textbook start from 1. Maybe that's because of this factor. We'll see. So factor, and this should be x to the power m. Right? Yeah. So let's use this first and see we got what the textbook is. And from 0 to infinity, e to the minus m times t, right? And dt, right? Just do expansion using this formula, right? And I think the idea is you multiply this to here, And basically, let's write another line. Minus 1. And then sum over m infinity e to the minus m plus 1 e dt. Right, and now we can shift this back to m. So m plus 1 go back to m, right? And then start with m equals to 1. Because the first term for this one is when m is 0, this is 1, right? So we can shift this called m and then start m to 1. So basically get rid of this one factor, just call it mt. That would be your textbook. Right, and now the idea is do another change of variable that is called t over m, right? And continue here. I'm not out of time. 14, right? And so basically change of variables t divided by m and t minus 1, right? And then the textbook writing it is something not as apparent. Basically, I mean, I cannot do that. In your textbook, it's kind of trying to do it in one step. The change of variable basically like using mt equals to t pi, right? Mt equals t pi. I need more steps. So basically, t is t pi over m. The dt is dt pi over m. Right, basically, and then right, just now using this, and then the t is t pi over m, and then c minus 1. I think now you actually take this, you need to take the summation, otherwise this doesn't make sense. Equals to 1 over gamma z sum over m boom 1 to infinity. So for each m, you define the change of variable with m. Okay, and that makes more sense. And then this is out. This is e to the minus t, and then this is d t over m d pi. This is d pi, right? And now you get all this m out of the summation. I have enough space. Let's continue up here. That is going to get all the m out. M 1 to infinity, get all the m. So you have m to z minus 1 in the denominator, but you multiply by m in the denominator. So altogether, you take out m to z, right? And that integration is dt 0 to infinity d pi z minus 1 e to the minus t pi dt pi. All right, and now this is you identify this as your gamma function. Right? This is the integral representation of the gamma function. This cancel with that. Right? And this one is just exactly the same definition of your gamma function. So you start from common function equals the integral. So basically forget about this equal sign. You start with this integral and then keep deriving up to here and using this definition. This is just your gamma z. Okay. And this integral also have this limitation because of the idea when t equals to 0, you want this to be convergent, the integral to be well defined. So you require z greater than -1. I mean that it's not so apparent because when t goes 0, there's another singularity here. Because at small t, et is roughly 1 plus t in the second order. So 1 minus 1 cancel this, there's an extra t in here. So make it more singular, so you require z greater than 1. So you have the same limit as the original definition, but later on we need to do some other thing to extend that. So the integral itself doesn't extend the domain. So we need to do something else to extend the domain of the